Here's a question. Work out the area of the triangle made by those coordinates. Now, I would suggest that before you watch any more of this, what I'm assuming is going to be quite a long video, I would suggest that you pause and give this a go. Try and find some way of doing it. I'm going to give you a hint before you do that though, which is to draw it just like I have here. I think that's going to help you. But more than this, if you answer this question correctly, then great, good work. But also, I'm going to set this challenge down here, which is that I think year 7s can solve this problem. I mean, I even think year 5s and 6s could solve this problem. And I think year 13s can solve this problem. And if you are a year 13 or 12 or 11, could you not only do it in whatever way you thought of, maybe using some advanced maths from year 10, 11, 12, 13, but could you also figure out how I'm expecting year 5, 6, or 7s to do this? You know, could you come up with other ways of doing this that perhaps are much, not easier, but rely on less heavy machinery in maths than the things that you might think to do first from GCSE or A-level? And also, if you are obviously someone much older, can you do this in lots of different ways? Like, how many different ways can you do this? Because that's kind of the point of this video, is I'm just going to show you all of the ways that I know how, which is quite a long list of ways. So think of as many as you can. If you want to, think of which ones you like the most and which ones are the most efficient and easiest. But yeah, I'm going to show you a lot of ways to do this, just because I think it's really fun, and it's really nice to just know a bunch of random maths that's going to help you do certain problems, because I'm going to use some maths that's not really used often for a question like this, but can be adapted to be so. And yeah, I think it's going to be really interesting. So without any further ado, I will get into it now. So what I'm going to do is I'm going to start with the easiest, quote unquote easiest methods. I'm going to do the methods that require the least heavy machinery. If you want an analogy, if solving this problem is a bit like putting a poster on your wall, I'm going to start with the most basic stuff possible, like just getting 2 pieces of blue tack and sticking it on the top. And then I'm going to head into more and more extreme methods, such as handcrafting a wooden frame to put it in with some perspex glass in front and so on. So I'm going to get into more and more serious and interesting methods as we go along in the video. But anyway, let's get into it. So the first method that I think even year 5s and 6s can do is just put a big box around the entire shape, just like so. And then you can use the boxes here to count how wide the box is and how tall it is, and so therefore you can work out that the area of this red rectangle here is 44. And then all you have to do to work out the area of this triangle here is to take away the 3 triangles that surround it. So this triangle here has base 11, height 3, so it's going to be a half times 11 times 3. This triangle here, which I actually did first, was height 4, width 1, 2, 3, 4, 5, 6. So half times 6 times 4, that's going to be 24, halved is 12. So just take that away. Then I think I'm going to do this triangle, 11 times 3, as I said. Take that away, which is 16.5, I think, because that's 33 halved yet. And this one is 1 times 5 times a half, which is 2.5. Take that away, and we get an area of 13. I think that's the most basic way that I found. But another quite nice, quite simple, using elementary maths method would be, instead of going kind of outside the shape, just go inside the shape. So split the shape into 3 triangles like so. Now if we start with this triangle here, like what I'm going to aim to do here is add together this triangle, and this triangle. So this triangle is obviously a half times 1 times 5. So that's going to be 2.5. Now this triangle here, if I consider this to be the base, has a base of 1, then the perpendicular height is just the distance from this point down to this base here, which is 1, 2, 3, 4, 5, 6. So this is just going to be a half times 1 times 6. And this triangle down here, if I consider this to be the base, 1, 2, 3, 4, 5, height is going to be 3. So it's going to be a half times 5 times 3, which is 7.5. And then, as I was saying here, half times 1 times 6 is going to be 3. Just add together 2.5, 7.5, and 3, and we get 13. So again, the area is definitely 13. We've done it in 2 quite nice ways. One more way that I wouldn't expect a year 5, 6, or 7 to know, but could certainly be done by a year 5, 6, or 7, is something called Pick's theorem, which is an incredible theorem, which says that for the area of any shape, it doesn't matter whether it's a triangle or not, if its vertices are on grid points, like these 3 are, then the area of that shape is given by I plus b over 2 minus 1. Now what are these things? Well, I is the number of points on the grid inside the shape. B is the number of points on the grid on the edge of the shape. And minus 1 is just minus 1. So let's count the number of points inside the shape. We've got 1 here. There's 1, there's one, and so on. Let's just keep going. Those are all the grid points in the shape, so I think that's, where's that? I think that's 12 of them, if I count up correctly. Points on the edge, so there's going to be 1, 2, 3, obviously, but there's also this one at 4. So I think there's going to be 4 of those. And so you just do I plus 4 over 2 minus 1, which is 12, plus 2 minus 1, which is 13. Really nice theorem here. Again, it works for any shape. No matter how many sides it has, as long as its points are on grid points, and of course as long as its sides are straight. If they're curved, then you have to break out pi and stuff like that, which we don't want to do. Anyway, next method is going to be a bit more complicated, so we're going to move more into the areas of key stage 3 and 4 maths now. So we're definitely going to be doing something a bit more complicated. This length is 11, I think, as we said before. This length is 3. I can do a little bit of Pythagoras to find x, right? 3 squared plus 11 squared is x squared from Pythagoras. So I think x is going to be root 130. And I'm going to do the same on the other two sides. I can't be bothered to do it properly. This is going to be 1 squared plus 5 squared, and this is going to be 6 squared plus 5 squared, I think. Plus 4 squared, sorry. You're going to get those two things there. So those are my 3 lengths of the sides of my triangle. And what I'm going to do is use Heron's formula, which again is not a formula that I'd expect many people to know off the top of their heads, but is very useful just to know. If a triangle has sides A, B, and C and perimeter P, then the area is given by this formula here. So okay, well A, B, and C are just root 130, root 26, root 25. P is the perimeter, so that's just the sum of these things. And so P over 2 is just the sum of those things divided by 2. And if you get out a calculator and you type this mammoth statement into it, just because I can't bother to round anything, there's P over 2 minus A, P over 2 minus B, P over 2 minus C, all underneath a root. When you press equals, your calculator might pause for a couple of seconds to work it out, but it will eventually give you exactly 13. So Heron's formula, very useful little formula. Maybe you want to bear it in mind because it is quite a nice little formula to use sometimes. Anyway, on to the next method. Again, getting into some more advanced maths now. If this is the point 46, this is the point 95, and this is the point minus 22, it turns out that actually there is just a formula for this. So if a triangle has vertices at x1, y1, x2, y2, and x3, y3, its area is just given by this formula. So you can just put these numbers in. I don't know why this root 130 is here. I don't really need it for this method. I can just put all of those points in to here. So x1, y1 is, so x1 is 4, y1 is 6, x2 is 9, y2 is 5. And likewise for the third point. Doesn't matter actually how you sort these out, it all ends up being the same thing in the end. Just carefully substitute in each one in the right place. So x1 is 4 from there, y2 is 5, y3 is 2, so those go in there, and then the rest of it is, I think I got it right. These straight lines, by the way, mean the absolute value of, so just in case this input here turns out to be a negative, which I think it does in my case, you just take the positive of that value, because of course area is positive. That's just a consequence of me choosing these vertices to be in whatever order I wanted. If I put them in a different order, I'd have ended up with a positive here and it wouldn't have made a difference. But anyway, half times 26 is indeed 13. So yeah, another useful little formula. I expect most of you probably knew this formula before watching this video, so I wouldn't be surprised at all if you had done that method. But yeah, so you can use that formula if you ever get a question like this. On to the next method. So again, I'm going to go back to my 3 side lengths here for this method here. So I'm going to use those, and I'm going to consider trying to find this angle here, theta. So what I'm going to do is I'm going to say, well, this length here is 3 and this one is 11, as we've said before. So this angle here, looking at this right-angled triangle, this angle here must be tan inverse of 3 over 11, right? Opposite over adjacent, which is 15.26. And this angle over here, because this distance is 6 and this one is 4, this angle up here must be tan inverse of 6 over 4. Again, opposite over adjacent, which gives me 56.31, which means this angle is going to be, well, there's a 90 degrees right there, isn't there? So this angle must be 90 minus those two, which is 18.43. And then, of course, I'm going to use a GCSE formula here, half AB sine C. So a half times the 2 widths of the triangle times the sine of the angle in between them. So I could have found any angle I wanted here and used the other 2 sides, but I'm just going to use these 2 sides. Put that in and you get, predictably, 13. There is another way to find that angle, of course. In fact, there's a couple of other ways. I'm going to do a few of them. Cosine rule would find this angle here. because I have three sides of the shape. So cosine is just a slightly more advanced adjustment on Pythagoras. Of course, you can see Pythagoras here, and then there's just the adjustment because this angle isn't 90. Let's find out what that angle is by putting root 26, because that's opposite the theta, on its own over here, and then use A and B as these two. Doesn't matter which order you do. Obviously these square out quite nicely, which is quite satisfying. Just working through the maths here, dividing by -2 and then dividing by the rest, you get cos theta as this, which means theta is cos inverse of that thing. I can't even be bothered to work out theta, even though I worked it out on the previous slide. All I'm going to do is say that the area is a half AB sine C, and then just do sine of that whole thing, because that's theta. Theta, of course, being C here as the angle. So I'm going to do half times A times B times sine of the angle, which I know to be cos inverse of this. Looks a bit messy. You can type that into a calculator and you'll get 13. Good. Moving on to the next method then. So next method is to say this distance is 3 and this distance is 11. We've looked at that kind of thing before, which makes the gradient of this line 3 over 11. For the same reason, I can say that the gradient of this line is, well, it has a rise of 6, sorry, it has a rise of 1, 2, 3, 4, and a run of 6. So that distance is, that gradient is 4 over 6, rise over run. And what I'm going to do is I'm going to use another formula here for this angle theta, which is I'm going to say that if you have the two gradients of the lines that bound your angle, you can use this formula here. Tan theta is m1 minus m2 over 1 plus m1 times m2. So using the two gradients here, I can work out the angle. So put those in, obviously. Well, tan inverse is obviously going to be theta. Put the 4/6 minus 3/11 in, and this in here, and do tan inverse of it, and you get theta is 18.43, as we found a couple of slides ago. And then, of course, using a half AB sine C, theta being C, of course, you can put theta into here, use the same two lengths we found earlier, root 52 and root 130, and we get 13 again. So just a different way to find the angle there, that method. Again, a really lovely little formula that it might be worth bearing in mind at some point if you want to. And yeah, this kind of opens up the door thinking about gradients to some more advanced algebraic techniques, particularly thinking about coordinate geometry, which we haven't really done a huge amount of so far in this video. We've done lots of trig and some other more basic methods, but again, let's work on this. So this is 3, this is 11. We already knew this gradient was 3/11ths, but actually let's work out the entire equation of this line, not just its gradient. So it goes through the point 9,5, and the equation of a line is y minus y1 equals mx minus x1. You can just use y equals mx plus c if you want to, but I'm going to use this. I've got my point 5 as my y coordinate and 9 as my x coordinate. Put that in, sort it out, and you eventually get this. And now there's a reason I'm going to make it look like this, rather than, you know, what you might be more used to, which is just dividing everything by 11 from here. The reason I want it to look like this is because I'm going to use yet another formula here. But before I do, this is the point 4,6. And what I want to do to this triangle is just do a half times base times perpendicular height. That's the first ever formula we learned for triangles way back in like year 3. Now this is the base, right? I can consider this the base, and I know it's root 130 because we did Pythagoras earlier. Now the perpendicular height would therefore be the length of the line that makes a right angle or perpendicular to this base here. So if I could work out the length of that line, I could just do a half times the length of this times root 130 for my half base times perp height. So how do I find the length of this line? Well, again, there's a formula for this that, you know, if you know, then you know, and it's great. And the formula is, if a line is of this form, so that's why I've put this line in this form here, and you have some point RS, which I'm going to use as 4,6, the perpendicular distance, or the shortest distance from that point to that line, is given by this formula here. Again, these absolute value lines showing that this is just positive no matter what it ends up being. And of course, if I put those numbers in, so A is minus 3, B is 11, C is minus 28, R is 4, and S is 6. If you just put all of that in, you get this. You sort it all out. I think maybe you can see where this is going with this root 130 here, because I'm not going to type that into a calculator because something really nice is going to happen here, which is when I use that length, which is this length, what happens, of course, is a half times base times perp height, half times this times this. The root 130s cancel, half times 26 is just going to be 13. So again, another nice method for finding the area of that triangle. In case you didn't know this formula, which, I mean, I'm guessing that Some of you may not. I'm assuming that most people watching the video would know that formula for sure off the top of their heads. But if you didn't know that formula straight up, there was a way to do this. It's kind of a similar method without it, which is again is get the equation of this line here, this point here, and then say, well, what's the equation of this line here, that perpendicular line we used before? What's the equation of that? Well, if this line dividing by 11 has gradient 3/11ths, because this is a perpendicular line, it must have gradient minus 11 over 3, the negative reciprocal. I know it also goes through the point 46, and so the equation of that line, again using y minus y1 equals mx minus x1, is going to be this. Sort that out, and you get something that looks a bit like this. And of course, my plan here is going to be if I can find this intersection point between this line, which has equation that, and this line, which has equation that. If I can find that intersection, then I could do Pythagoras on this point and this point to find the distance between them. That, of course, will be my perpendicular height, and then I can go back to this formula with the base, half, and perpendicular height that I'll find. So let's find this coordinate here. And of course, to do that, I'm going to set this line equal to this one. This looks really messy, but what I'm going to do is times everything by 11 and times everything by 3 at the same time. So essentially just times both sides by 33, and you get this, which is much nicer. Add 121x to both sides, take away 84, divide by 130, which gives you 4.6. Put 4.6 into either one of these, it doesn't matter, you get y as 3.8. So this is the point 4.6, 3.8, and now I'm going to have to do some Pythagoras here to find the length of this. So it's going to be, well, the x distance is just 0.6, because it goes from 4 to 4.6. The y distance is 2.2, difference between those things, root them, or add them together, root them, and when you type that into a calculator, half times base times perpendicular height, you get, predictably, again, 13. So okay, that's one of the more involved and tough methods. Actually might have been the method that some of you did, because it's the one that most heavily relies on GCSE maths, I think. Though I think lots of you might have just done cosine rule and found the angle and stuff like that. But anyway, moving on. So again, I'm going to use the lengths of the lines for this next trick. But actually what I'm going to do is I'm going to consider some, so this next couple of methods is going to be, I think, largely rooted in A-level maths. In fact, thinking about it, it's going to be completely A-level maths, almost. So I'm representing a line here because I'm going to think about this in terms of vectors now. So this, from this point to this point, the vector, well, it's 11 across, as already discussed, and 3 up. So that's the vector 11, 3. And likewise, this line here, it's 6 across and 4 up. So that's the vector 6, 4. And if you haven't seen dot products yet, you're about to learn something. The dot product of two vectors, a dot b, is defined to be the modulus of a times the modulus of b times cos theta, where theta is the angle between the two vectors. So I can find theta using this formula here. The modulus of a, by the way, is the length of it, which I already know to be 130, and the modulus of b can be root 52. So 11.3.64 is root 30 times root 52 times cos theta. To do the dot product, you just multiply across and add up the results, so 66 plus 12. If this maths looks familiar, it's because essentially the cosine rule is just this. So if you scroll all the way back in the video, you'll see that cosine rule got me this as well. Anyway, do cos inverse, you find this, then do, of course, a half AB sine C, and you can find that the area is, of course, 13. There's another type of multiplication, though. A lot of you might not be aware, but when you start talking about vectors, there's actually more than one type of multiplication, and the other big one is called cross multiplication. So cross multiplication, which we give by this cross sign, or at least the modulus of cross multiplication, gives the area of the parallelogram between the vectors. Now, what do I mean by that? Well, I mean if you copy this vector out here and copy this vector out here to make yourself a parallelogram, when you cross the two vectors that you've kind of doubled to form that with, the modulus of that cross gives you the area of the parallelogram. Now, I'm not interested in the area of that, I'm interested in the area of the triangle, but of course the triangle is just half of that. So if I half this modulus of a cross b, I'm going to get the area of the triangle. Now, there's one small problem in this plan, which is the cross product is only defined for 3-dimensional vectors and higher. It's not defined for two-dimensional vectors, which is, of course, what I've got. I've got vectors in x and y. But of course I can fix that because I'm super big brain. I can just draw in a z-axis. There it is. Look, it's definitely a z-axis because it says z on it. I can draw in a z-axis and I can say, well, this vector here is definitely 11 across in the x dimension and 3 up in the y dimension, and it's just not moving in the z direction, right? So actually this vector is not 11, 3, it's 11, 3, 0, right? It's still going 11 across in the x direction, still going 3 up in the y direction, and it's just not going anywhere in the z direction. So it's 11, 3, 0, and likewise this vector is 6, 4, 0, and now I can happily do the cross product and then halve the modulus of the result. So the cross product here, if you haven't seen cross products, all you have to do is transpose these into a 3x3 determinant matrix and find the determinant of that matrix, I should say, with ijk on the top. This goes really nicely because these zeros help you out a lot, because the first result is clearly going to be 0, 3 times 0, 4 times 0. The second result is also going to be 0, 11 times 0, 6 times 0. It's only the third result that's going to matter. So 11 times 4 is 44, minus 6 times 3, which is 18. 44 minus 18 is 26. Of course, the modulus of 26k is just 26, and the modulus or absolute value of 26 is just 26. Halved is of course 13, so we arrive nicely at our answer. Okay, so one more method I think that I've got here, in fact I've got a couple more methods I think, but one more which relies on A-level maths. Different type of A-level maths here. Again, if we work on the equation of this line here, which is y equals 3 over 11x plus 28 over 11, I think I found that before earlier in this video. I'm not going to go through a massive amount of effort to find the equations of these lines. I'm just going to state them. I'm sure if you're still watching this video at this point that you can probably find the equations of these lines yourself. So I'll just say that I've done that. Now what I'm going to do is I'm going to split this triangle into two. I'm going to think about this triangle over on the left-hand side, the red line, and I'm also going to think about this triangle on the right-hand side. I'm going to work out each triangle individually, and then I'm going to add them up. Maybe if you've done year 12 and year 13 maths, you can see where I'm going with this, because if you haven't done the topic this is going to be, I'm sure you're going to be very confused as to why I'm doing this. But if you've seen this topic, I think you know where I'm going with this. What I'm going to do is I'm going to say, well, between here and here, if I draw two more lines down here, the area of this blue triangle here is the integral between 4 and minus 2 of the top line, 2 over 3x plus 10 over 3, minus the integral between 4 and minus 2 of the bottom line, 311x plus 28 over 11. So that's going to be the blue area. Of course, I can tidy this up because they're over the same bounds, which means I can just combine the integrals together. To do that, I'm going to times this one by 11 over 11 and this one by 3 over 3. And now I can do 22 minus 9 is 13, 110 minus 84 is 26. And now I can just take out a 33rd. And actually now I can take out 13. And I end up with quite a nice integral to do. If I take out 13 from that, I just get the integral of x plus 2 over this bound. So that's the blue area, and I can do that integral a bit later. First, let's talk a bit more about, let's just there again, let's talk more about the red area now. Very similar logic, but this time I'm going to be integrating between 9 and 4. I'm going to do this line first, of course, because it's on top, and then take away this line. So similar kind of idea here. Times this one by 11 over 11, this one by 5 over 5. Again, it's the same bounds for each integral, or the same limits, I should probably say. So I can put these together. Minus 11 minus 15 is minus 26. This minus that is that. Take out a 55th. Slightly worse integral to do here, it looks like, but it should be okay. So that's the red area. That's the blue area that I found before. Of course, the area of the triangle is just the red plus the blue. So all I have to do is put those things together. Now I'm actually going to do some integrating, I think. So, of course, this integrates to a half x squared. This integrates to 2x. Put 4 and minus 2 into there. Likewise, this one integrates as well nicely. Put those in. Ends up being a bit messy, but that's okay. Simplify the inside of the brackets first, of course. You get this. And now here's a nice little thing to do without a calculator. Nice little exercise, I should say, to do without a calculator. Can we do this without one? Well, yeah. If you just take out 1/11th to leave this, 18 divided by 3 is clearly 6. That's fine, so I can times that by 13. 325 divided by 5 I can do easily with a bus stop. Add those two things together. Miraculously, 143 divided by 11 turns out to be 13. and that's another method you can do to find the area of this triangle. One more method, and I should warn you before we get into this method that this is only for university math students and above. I think you'll be very lost with this method if you haven't completed a significant amount of post-secondary or high school maths education. But this last method is when you highlight the question and press Control-C. Then you go into whatever web browser you prefer using, find Wolfram Alpha, and then press Control-V. Now, Wolfram Alpha gets a bit confused by lots of words, so let's just get rid of made by coordinates, and let's just get rid of work out and just type enter. And I think I've removed enough words so that it won't be too confused by this. This is what my maths degree is for, by the way. Being able to get rid of the correct nonsense words. I think Wolfram Alpha will give me the answer of 13, which is excellent. So really advanced method there that it really takes some university level maths to really understand this last method. But well done for sticking with me. I can't remember how many different ways that was in total, but I think it was quite a few, and I hope you learned some new and interesting maths during this video.